Hello, today our topic is basic spatial filtering. First, what is meant by filter? Applying the filter to an image is another way to modifying the image, and the difference compared to point operation is the filter use more than the one pixel to generate a new pixel value. For example, smoothing filter which replace a pixel value by average of its neighboring pixel value. Filtering is a technique for modifying or enhancing an image. Spatial domain operation or filtering the proceed value of the current pixel proceed value for the current pixel depend on both the itself and surrounding pixel. Here, hence, filtering is the neighborhood operation in which the value of any given pixel in the output image is determined by applying some algorithm to the values of the pixel in the neighborhood of the corresponding input pixel. A pixel's neighborhood is a sum set of pixels defined by their locations relative to that pixel. Spatial filtering is a process by which we can alter the properties of an optical image by selectively removing the certain spatial frequency that make up an object. For example, filtering video data received from a satellite and space probes or removal of raster from a television picture or scan image. Why do we use a spatial filtering? Spatial filtering is a commonly used to clean up the output of lasers, removing aberrations in the beam due to imperfect, dirty, or damaged optics, or due to variation in the laser gain medium itself. Then, what are the fundamentals of spatial filtering? We introduce the several basic concepts underlying the use of the spatial filters for image processing. Spatial filtering is the one of the principal tool used in the field for a broad spectrum of applications. So it is highly advisable that you develop a solid understanding of this concept. As mentioned at the beginning of this chapter, the example in this section deal mostly with the use of spatial filter for the image enhancement. The spatial filtering is used in a broad spectrum of the image processing applications. So, a solid understanding of filtering principle is important. The name filter is borrowed from a frequency domain processing where the filtering refer to passing, modifying or rejecting specified frequency component of an image. The name filter is borrowed from frequency domain processing where the filtering is referred to accepting or passing or rejecting certain frequency component. For example, a filter that passes low frequency is called as low pass filter. The net effect produced by a low pass filter is to blur or smooth an image. We can accomplish a similar smoothing directly on the image itself by using spatial filters, also called spatial masks, kernels, templates, and windows. In fact, there is one-to-one correspondence between linear spatial filters and filters in the frequency domain. However, a spatial filters offer considerably more versatility because as you will see later, they can be used also for non-linear filtering, sometimes we cannot do in the frequency domain. If the operation performed on the image pixels is linear, then the filter is called as a linear spatial filter. Otherwise, the filter is non-linear spatial filter. We will focus attention first on linear filter and then introduce some basic non-linear filter. Then, what is linear spatial filtering? A linear spatial filter performs a sum of product operations between an image f and the filter kernel w. The kernel is an array whose size defines the neighborhood of operation and whose coefficient determines the nature of the filter. Other terms used to refer to a spatial filter kernel are mask, template, and window. We use the term filter, kernel, or simply kernel. A spatial filter consists of a neighborhood, typically a small rectangles, and a predefined operation that perform on the image pixel encomposed by the neighborhood. Filtering creates a new pixel with the coordinates equal to the coordinates of the center of the neighborhood and whose value is the result of the filtering operation. A proceed, that is a filter image, is generated as the center of the filter visit each pixel in the input image. If the operation performed on the image pixel is linear, then the filter is called as a linear spatial filter. Otherwise, the filter is non-linear. Let us consider the figure 1 illustrates the mechanism of linear spatial filtering using a 3 by 3 neighborhood. At any point x, y in the image, the response g of xy of the filter is the sum of the product of the filter coefficients and the image pixels encompassed by the filter. It is given by the equation form, that is g of x comma y is equal to w minus 1, that is w is nothing but the kernel, f of x minus 1 comma y minus 1 plus w is bracket minus 1 comma 0 into f of x minus 1 comma y plus dash 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 plus w in bracket 0 comma 0 f of xy plus dash 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 plus w 1 comma 1 f of x plus 1 y plus 1. Observe that the center coefficient of the filter w of 0 0 aligns with the pixel at the location x comma y. For a mark size m by n, we assume that m is equal to 2a plus 1 and n is equal to 2b plus 1, where a and b are the positive integers. This means that our focus in the following discussions is on the filter of our size, with the smallest being of the size 3 by 3. As a coordinate x and y vary, the center of the kernel moves from pixel to pixel, generating the filter image. G is the process. A filter pixel value typically is assigned to a corresponding location in a new image created to hold the result of filtering. In general, the spatial filtering of an image m by n with a filter of a size small m by n is given by the following expression, that is g of xy is equal to summation of s is equal to minus a to a into summation of t is equal to minus b to b w of s comma t f of x plus s comma y plus t. This means that our focus is on kernel of our size in both the coordinate directions, where x and y are the varied so that the center, that is the origin of the kernel, visit every pixel in f once. In a similar manner, the convolution of w of xy and f of xy is denoted by w of xy convolution f of xy is given by the following expression, that is w of x comma y convolution f of x comma y is equal to summation of s is equal to minus a to a summation of t is equal to minus b to b w of s comma t into f of x plus s y plus t, or x minus s y minus t. We can use plus or minus. We are discussing all about this figure, that is the mechanism of linear spatial filtering using 3 by 3 filter marks. We have already discussed before. Then our next topic is spatial correlation and convolution. There are two closely related concepts that must be understood clearly when performing the linear spatial filtering. One is the correlation and the other is the convolution. Correlation is the process of moving a filter mask over the image and computing the sum of the product at each location exactly. The mechanism of convolution are the same except that the filter is first rotated by 180 degree. The best way to explain the difference between the two concepts is by example. Convolution and correlation are similar mathematical operation. Correlation is also a convolution operation between the two signals, but the signal is the functional inverse. So in the correlation process, one of the signal is rotated by 180 degree. This is the basic difference between the convolution and correlation. Let us consider the one example that shows the spatial correlation and convolution. The figure A shows a 1D function f and a filter w, and the figure B shows the starting position to perform the correlation. The first thing we note is that there are part of the function that do not overlap. The solution to this problem is to pad f with enough zeros on the either side to allow each pixel in w to visit every pixel in f. If the filter is of size small m, we need m-1 zeros on the either side of f. While the figure C shows a properly padded function. The first value of the correlation is the sum of the product of f and w for the initial position shown in figure C. The sum of the product is 0. These correspond to a displacement, that is x is equal to 0. To obtain the second value of the correlation, we shift w 1 pixel location to the right, that is displacement of x is equal to 1, and compute the sum of products. The result again is 0. In fact, the first non-zero result is when x is equal to 3, in which the case the 8 in the w overlaps and 1 in the f, and the result of the correlation is 8. Proceeding in this manner, we obtain the full correlation result in figure G. Note that it took 12 values of x, that is x is equal to from 0 to up to 11, to fully side w and past f, so that each pixel in w visited every pixel in f. Often we like to work with the correlation array that are the same size as f, in which the case we crop the full correlation to the size of the original function as shown in figure H. There are two important points to note from the discussion in the preceding topic. That first, correlation is a function of a displacement of the filter. In other words, the first value of correlation corresponds to the 0 displacement of the filter, the second corresponds to the 1 unit displacement, and so on. The second thing to notice is that correlating a filter w with a function that contains all the zeros and a single one yields the result that is a copy of w but rotated by 180 degree. We call a function that contains a single one with a rest being zeros discrete unit impulse. So we conclude that correlation of a function with a discrete unit impulse is a rotated version of the function at the location of the impulse. The concept of convolution is a cornerstone of a linear system theory. A fundamental property of convolution is that convolving a function with a unit impulse yields a copy of a function at the location of the impulse. We saw in the previous discussion that correlation yields a copy of function also but rotated by 180 degree. Therefore, if we pre-rotate the filter and perform the same sliding sum of the product operation, we should be able to obtain a desired result. At the right column of the figure shows this indeed is the case. Thus, we see that to perform the convolution, all we do is rotate one function by 180 degree and perform the same operation same operation as in correlation. As it turned out, it makes no difference which of the two functions we rotate. This is all about the convolution. And then this figure shows that the correlation and convolution of 2D filter with a 2D discrete unit impulse. The correlation operation in 2D is a very straightforward. We just take a filter of a given size and place it over a local region in the image having the same size as a filter. We continue this operation shifting the same filter through the entire image. This also help us to achieve two very popular properties. That is, first one is a translation invariance and second one is a locality. In translation variance, our vision system should to be sense, respond or detect the same object regardless of where it appears in the image. And the second one is a locality. Our vision system focuses on local regions without regards to what else is happening in other parts of an image. The cross correlation function has a limitation or characteristics property that when it is applied on the discrete unit impulse, that's a 2D matrix of all the zeros and just single one, yield a result that is a copy of the filter but rotated by the angle of 180 degree. And the convolution operation is very similar to the cross correlation operation, but has a slight difference. That is, in the convolution operation, the kernel is first flipped by an angle of 180 degree and then applied to the image. The fundamental property of the convolution is that convolving a kernel with a discrete unit impulse yield a copy of the kernel at the location of the impulse. We saw in a cross correlation section that correlation operation yield a copy of the impulse but rotated by an angle 180 degree. Therefore, if we pre-rotate the filter and perform the same sliding sum product operation, we should be able to obtain the desired result. This figure shows for a filter of size m by n, we pair the image with a minimum of m-1 rows of zeros at the top and the bottom and n-1 column of zeros on the left and right. In this case, m and n are equal to 3. So we pad f with the 2 rows of zeros above and below and 2 columns of zeros to the left and right. The figure B shows as shown in figure B. Then next, figure C shows the initial position of the filter mask for performing the correlation, and figure D shows the full correlation result, while the figure E shows the corresponding crop result. Note again that the result is rotated by 180 degree. For the convolution, we pre-rotate the mask as before and repeat the sliding sum of the product we just explained. Figure F through H shows the result. You see again that the convolution of the function with an impulse copies the function at the location of the impulse. It should be clear that if the filter mask is symmetric, correlation and convolution yield the same result. If instead of containing a single one, image f in the figure had contained a region identically equal to w, that is a kernel operator, the value of the correlation function after normalization would have been maximum, then w was centered on that region of f. Thus, as you will see that correlation can be used also to find the matches between the images. Summarizing the preceding discussion, in equation form, we have that the correlation of the filter, that is w of x comma y of the size m by n with an image f of x comma y denoted as the w of x comma y convolution f of x comma y is given by the equation listed at the end of the last section, is that is w of xy convolution f of xy is equal to summation of s is equal to minus a to a, summation of t is equal to minus b to b, w of s comma t f of x plus s y plus t. This equation is evaluated for all the values of the displacement variables x and y, so that all the elements of w visit every pixel in f, where we assume that f has been padded appropriately. As explained earlier, a is equal to in bracket m minus 1 by 2, b is equal to in bracket n minus 1 by 2, and we assume for the notational convenience that m and n are odd integers. In a similar manner, the convolution of w of x comma y and f of x comma y is denoted by, that is w of x comma y convolution f of x comma y is given by the following expression, that w of x comma y convolution f of x comma y, that is summation of a is equal to minus a to a, summation of t is equal to minus b to b, w of s comma t f of x minus s y minus t, where the minus sign of the right flip f, that is rotate it by 180 degree. Flipping and shifting f instead of w is done by the notational simplicity and also to follow the convention. The result is the same. As with the correlation, this equation is evaluated for all the values of displacement variables x and y, so that every element of w visits every pixel in f, which we assume has been padded appropriately. We are already discussed about, if we want to perform the correlation, we input the w into the algorithm for convolution. We input w rotated by 180 degree. The reverse is true if an algorithm that implements in the equation form is available instead. As we mentioned earlier, the convolution is the cornerstone of linear system theory. The property that the convolution of a function with a unit impulse copies a function of the location of the impulse plays a central role in a number of important deviations. Finally, we point out that the terms convolution filter, convolution mask, or convolution kernel in the image processing literature, as a rule, these terms are used to denote a special filter and not necessarily that the filter will be used for the true convolution. Similarly, the convolving a mask with an image often is used to denote the sliding and the sum of product process we just explained, and does not necessarily differentiate between correlation and convolution. Rather, it is used generally to denote either of the two operations. This implies that terminology is a frequent source of confusion. In short, the convolution and the correlations are similar mathematical operation, but while the correlation is also the convolution operation between the two signals, but one of the signal is a functional inverse. So in correlation process, one of the signal is rotated by 180 degree. This is the basic difference between the convolution and correlation. Shortly, the convolution is the process of adding each element of the image to its local neighbors, weighted by the kernel. This is related to form a mathematical convolution. The matrix operation being performed, the convolution is not a traditional matrix multiplication despite being similarly denoted by. While the correlation is the process of moving a filter mask, often referred to as a kernel, over the image and computing the sum of products at each location. Correlation is the function of displacement of the filter. This is all about the basic of correlation and convolution. It is important to represent the spatial filtering. In short, the kernel means what? In image processing, a kernel, convolution matrix, and or mask is a small matrix used for blurring, sharpening, embossing, edge detection, and more. In image processing, the kernel is main thing. Then our next topic is vector representation of linear filtering. When interest lies in the characteristics response R of a matrix of a mask, either for a correlation or convolution, it is convenient sometimes to write the sum of the product as, that is R is equal to W1Z1 plus W2Z2 plus dash 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 plus up to WMNZMN. It is also write in the form of, that is summation of k is equal to 1 to mn w of k z of k, that is wt z, where ws is the coefficient of an m by n filter and the zs are the corresponding image intensity encompassed by the filter. The above equation is for correlation. We use the mask as given. To use the same equation for the convolution, we simply rotate the mask by 180 degree. We are discussed in a last section. filter mask. Then next topic is how we can generating the special filter mask. Generating an m by n linear special filter requires that we specify m into n mask coefficients. In turn, these coefficients are selected based on what the filter is supposed to do, keeping in mind that all we can do with a linear filtering is to implement a sum of a product. For example, suppose that we want to replace the pixel in an image by the average intensity of a 3 by 3 neighborhood center on those pixels. The average value at any location x, y in the image is the sum of the 9 intensities values in the 3 by 3 neighborhood center on x, y divided by 9, letting zi I is equal to 1 to up to 9 denote this intensity. The average is, that is r is equal to 1 upon 9 summation of I is equal to 1 up to n z of I. But this is same in equation, that is we in this equation with the coefficient values wi is equal to 1 by 9. In other words, a linear filtering operation with a 3 by 3 mask whose coefficients are 1 by 9 implements the desired averaging. As we discuss in the next section, this operation result in image smoothing. We discuss in the following section a number of each filter mask based on this basic approach. In some applications, we have a continuous function of two variables and the objective is to obtain a special filter mask based on that function. For example, a Gaussian function of two variables has the basic form, that is h of x, y is equal to e raised to minus x square plus y square upon 2 sigma square, where sigma is the standard deviation. As usual, we assume that the coordinate x and y are the integers. To generate, say that is a 3 by 3 filter mask from this function, we sample it about its center, that thus w1 is equal to h of minus 1 comma 1, w2 is equal to h of minus 1 comma 0 dash 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 up to w9 is equal to h of 1 comma 1, and m by n filter mask is generated in a similar manner. Recall that the 2D Gaussian function has the bell shape and that the result deviation, that is the standard deviation, control the tightness of the bell. For generating a non-linear filter requires that we specify the size of neighborhood and operation S to be performed on the image pixel contained in the neighborhood. For example, recalling that the maximum operation is non-linear, a 5 by 5 max filter center at an arbitrary point, that is x, y of an image, obtains the maximum intensity values of 25 pixels and assigns that the values of location x, y in the proceed image. Non-linear filters are quite powerful and in some applications can perform the functions that are beyond the capability of linear filters. In short, what is meant by spatial filtering? The concept of masking is also known as a spatial filtering. Masking is also known as a filtering. Basically, the spatial filtering modifies an image by replacing the value of each pixel by a function of the values of pixel and its neighbors. If the operation performed on the image pixel is linear, then the filter is called as linear spatial filter. Otherwise, the filter is non-linear spatial filter. In short, what is meant by linear filtering? Linear filtering is the filtering method in which the value of the output pixel is a linear combination of neighboring input pixel. It can be done with a convolution, for example, mean or average filters or a Gaussian filtering. And what is meant by non-linear filtering? Non-linear filtering is the one that cannot be done with a convolution or Fourier multiplication. A sliding median filter is the simple example of non-linear filter. In linear spatial filtering, the spatial mask convolution process is used. In nonlinear filtering, the ordering mechanism is used to produce the output pixel, that is to replace the center pixel. This is all about the in short summary of linear filtering and nonlinear filtering. In short, what is meant by convolution and correlation? Correlation is also a convolution operation between the two signals, but one of the signal is functional inverse. Correlation is measurement of simplicity between two signal or sequence, while the convolution is the measurement of the effect of one signal on the another signal. The mathematical calculation of correlation is same as the convolution in time domain, except that the signal is not reversed before the multiplication process. Basically, the convolution is the process of adding each element of the image to its local neighbors weighted by the kernel. Kernel means while in short, the correlation is the process of moving a filter mask, often referred to as a kernel, over the image and computing the sum of product at each location. The correlation is the function of a displacement of the filter. This is all about the basic summary of this lecture. In this lecture, we have discussed the topic like basic spatial filtering. What are the fundamental of spatial filtering? What is the mechanism of the spatial filtering? Spatial correlation and convolution. Vector representation of linear filtering. What is meant by linear filtering and non-linear filtering? And how we can generating the spatial filter marks. In this lecture, we have covered all these topics. Thank you. Thank you again.